Hello, Assalamu alaikum everyone. So today we're going to be starting off with the very first chapter of the A-Levels Physics syllabus, which is physical quantities and units. Mentioned on the screen are the learning objectives that we will be covering in this video. What exactly is physics? Physics is the study of physical quantities. There are two types of physical quantities. There are basic quantities and then there are derived quantities. When we talk about the basic quantities, a basic quantity is the seed from which the plant of derived quantities grows. So we could say that basic quantity is the root of the derived quantity. A basic quantity is essential for a derived quantity to exist. So we're going to go through some of the basic quantities. They include length, which is measured in meters. There is mass, which is measured in kilograms. There is time, which is measured in seconds. There is electric current, which is measured in amperes. There is temperature, which is measured in Kelvin. These are the basic quantities we're going to be covering in our S syllabus. And then in the A2 syllabus, we'll cover amount of substance, which is measured in moles. There is also another basic quantity which is light intensity and its units is candela. However, that is not a part of the A-level syllabus. Moving on to the derived quantities. They include area, volume, speed, acceleration and density. Now, as we dive deeper into the derived quantities, we know that area is a quantity that has been derived, and the formula of area of a cube, for example, is length square, right? So we are using the basic quantity of length to derive this quantity. Similarly, the volume of a cuboid has a formula of L cube, length cube. So we are again using the basic quantity of length in order to derive the derived quantity of volume. Now moving on to speed, we know that speed is distance upon time, right? And we know that the distance itself is basically length. So we're using the basic quantity of length and time in order to derive the quantity of speed. Similarly, in acceleration, we're using the same two quantities again, length and time. In density, the formula of density is basically mass upon volume, right? So mass is a basic quantity and then volume is also derived from length. So we're using mass and length in order to derive the quantity of density. So this is how the derived quantities are basically composed of basic quantities. Now we move on to the rules for indices. So if you're multiplying a with a power of m with another a with a power of n, then a would remain the same and the powers m and n would get added. Similarly, if ab is being multiplied by the power of m, then it would become am and b to the power of m as well. Now, if we're basically dividing a by b and all of this is being multiplied by the power of m, then we're going to be multiplying each a and b by m separately as well. Now if we're dividing the two powers, for example, a to the power of m is being divided by a to the power of n, then it's going to be a to the power m minus n. So basically the powers would get subtracted, and lastly if it is a upon m, it would become a and minus m, so it would be inverse. So this is what happens, and these are some specific rules for indices. We just need to keep these in mind for further calculations. Now we'll learn how to derive some quantities from the physical quantities they're composed of. So the first one is force. The units of force are newtons, and the formula of force is equals to mass into acceleration, right? We know that mass has the units of kilograms and acceleration has the units meter square minus 2, right? So basically when we multiply both of these, it's going to become kg ms minus 2. So basically 1 Newton would be equal to 1 kg ms minus 2. Base units or the basic units of Newton are kg ms minus 2. Moving on to the next quantity, which is work done or energy. So we know that the units of work done or energy are always joules, right? And we know that the formula of work done is force multiplied by displacement. So work done is basically the product of displacement and force. So basically we derived the units, the base units for force, which were kg ms minus 2. Now we will multiply the kg ms minus 2 by meter, because meter is basically the unit for displacement, right? Because displacement is length. So we're going to multiply the base units of force by the base unit of displacement, which will form kg m square s minus 2. So we can know that 1 joule is basically equal to 1 kg ms minus 2. Similarly, if we take energy in terms of gravitational potential energy or kinetic energy, we can again find out that these same units are basically the base units for energy, right? So the formula for gravitational potential energy is mgh. And the formula for kinetic energy is 1 upon 2 mv square. All of this is assumed knowledge from your O level. So yeah, so we know that the formula of gravitational potential energy is mgh, right, which is basically mass multiplied by acceleration due to gravity multiplied by height. Since the base units of mass are kilograms, the units of acceleration are ms minus 2, and the unit of height is basically meter, because height is length, right? So the units would be meter. Now if we multiply all three of these, it would again form kg m square s minus 2, which we earlier derived when we used the formula of work done, which was force into displacement. Moving on, if we use the formula of kinetic energy, we can again derive the base units. For example, the formula of kinetic energy is 1 upon 2 mv square. So we basically use mass and we use velocity. Now 1 upon 2 has got nothing to do in the equation when we're forming the base units, so we're going to ignore that. We're just going to multiply the unit for mass, which is kilograms, with the unit for velocity, which is ms minus 1, and we're going to square the unit for velocity because it is mv squared, right? So the velocity is being squared, so the units would also get squared. So it's also going to form kg m square s minus 2. In this way, we can basically derive the base units for work done or energy. Going on to power, from O levels we've learned that power is basically the rate of doing work, right? So the formula is work done upon time, and the units of power are watt, right? So basically, when we're basically finding out the base units of power, we're going to use the same formula, which is work done upon time. Earlier we derived the unit for work done, which was kg m square s minus 2, and we divided by time, which is basically seconds. So we find out the base units for power, which are kg m square s minus 3. So from this we know that 5 watts would be equal to 5 kg m square s minus 3. Now moving on to voltage. The units of voltage are basically volt, right? And we know that power is equals to current into voltage. P is equals to IV. We also learned this from O levels, that P is equals to IV. So power is equals to current into voltage, right? So if we rearrange the formula and make voltage the subject, we find that the formula of voltage would be power upon current. And earlier we derived the units for power, which were kg m square s minus 3. We'll divide it by the unit for current, which is ampere, and so we find out the base units of voltage, which are kg m square s minus 3 a minus 1. So now we know that since 1 volt would be equal to 1 kg m square s minus 3 a minus 1, so 5 volt would be equal to 5 kg m square s minus 3 a minus 1. Moving on to the fifth quantity, which is resistance. Now basically we've known it from O levels as well, that V is equals to IR. So we rearrange the formula, make R the subject, so we know that resistance is basically voltage divided by current, right? And the units for resistance are ohm. So when we divide voltage by current, earlier we found out the units for voltage were kg m square s minus 3 a minus 1. Now we divide that by current, so we divided by A, so that becomes kg m square s minus 3 a minus 2, because the A which is getting divided would go up, and it's going to make up A minus 2 from A minus 1, right? So it becomes 1 ohm is equals to 1 kg m square s minus 3 a minus 2. So 5 ohms would be equal to 5 kg m square s minus 3 a minus 2. Now as we move on to pressure, we've always known that pressure is basically force upon area, and the units of pressure are pascals, right? So now we know the units for force are kg ms minus 2. We divide them by the units of area, which are m square, meter square, and now we find out that the units of pressure would end up being kg m minus 1 s minus 2, right? So 1 pascal would be equal to 1 kg m minus 1 s minus 2. So 5 pascals would be basically equal to 5 kg m minus 1 s minus 2. Moving on to the seventh quantity, which is charge. Now we know that the units of charge are coulomb, and the formula for charge is IT. Q is equals to IT. What is I? I is current and T is time. So basically we multiply the units for current, which are ampere, with the unit for time, which is seconds. And so we find out that the base unit for charge would be AS, ampere second, right? So since 1 coulomb would be equal to 1 ampere second, 5 coulombs would be equal to 5 ampere seconds. Now moving on to the last quantity, which is specific heat capacity. Specific heat capacity has the units of joules per kg per Kelvin, and the formula for specific heat capacity is equals to Q is equals to MC, change in temperature, right? So Q is basically the energy here. We rearrange the formula, make specific heat capacity the subject, and so we find out that the formula to find the specific heat capacity is Q upon M into change in temperature. We know that the units for energy were basically kg m square s minus 2. We divide the unit of energy by the unit of mass, which is kilograms, and the unit of temperature, which is Kelvin. So when we divide both of these quantities, we get m square s minus 2 k minus 1, which is basically the base units for the specific heat capacity. Now here's a quick overview of what is the physical quantity, what is a derived quantity, and what is a basic quantity. So we know that the physical quantity is one which can be measured and has units, right? It can be measured and it has units. What is a basic quantity? A base quantity is one which cannot be expressed in terms of other physical quantities, because it is a base which is used to derive other quantities, right? So it cannot be expressed in terms of other physical quantities because it's the base itself. A derived quantity, however, is one which can be expressed using one or more base quantities. So as we derived the quantities earlier, we came to know that those quantities were basically composed of the different base quantities, right? So a derived quantity is one which can be expressed using one or more base quantities. So that's about it.
Okay, so now we've been given a question. It says f is equals to q square upon 4 pi x r square, and then there is f is equals to y I square upon 2 pi d. The f in this question represents force. The units are kg ms minus 2. The q represents charge. The units are as. The r represents radius. The units are meters. The I represents electric current. The units are ampere. And the d represents the diameter, so its units are meter. In this question, it says find the base units of quantity xy and also identify which quantity it is. So first of all, we'll take both the equations we've been given above and we'll make x and y the subjects respectively. After making them the subjects, instead of writing the physical quantity, for example charge or for example force, we're going to write down their respective units instead. So for example, it says x is equals to q square upon 4 pi f r square. In this equation, first of all, we'll eliminate the 4 pi because we know that 4 pi does not have any units, so it is insignificant to us. So we'll remove the 4 pi and so it will just be x is equals to q square upon f r square. So now instead of q, we'll substitute its respective units. So the units of q, charge, are as, right? So instead of q square, we'll write as square. Instead of f, we'll write kg ms minus 2. And instead of r square, we'll write m square, meter square. So after doing the right math, we'll come to the conclusion that x is equals to a square kg minus 1 s4 m minus 3. Now looking at the second equation we'd been given, we'll again make y the subject. After making y the subject, we'll quickly eliminate the 2 pi because it does not have any units, so it is insignificant to us. After eliminating that, we'd have df upon I2. Now we know that d is the diameter, so the units are meters. So instead of d, we'll write m. Instead of force, we'll write kg ms minus 2. And instead of I square, I is current, right? So the units are ampere. So instead of I square, we'll write a square. And so after doing the right math, after crossing out everything, we'll get that y is basically kg m square s minus 2 a minus 2. So now we have the base units of x and y each. The question said find the base units of quantity xy and identify which quantity it is. So now we have to multiply both of these x and y in order to find out the base units of xy. So basically we'll multiply the a square kg minus 1 s4 minus 3 m minus 3, which were the base units of x, with the base units of y, which are kg m square s minus 2 a minus 2. And after cutting down and cutting everything, we'll basically find that xy is equals to m minus 1 s square. We know that the units of acceleration are ms minus 2, right? So m minus 1 and s2 is basically the reciprocal of ms minus 2. So we know that xy is the reciprocal of acceleration. In this way, we'll be able to solve questions like these. Now here we'll be moving on to the homogeneity of an equation. So basically, if the base units of all the terms on the right hand side of any equation are identical to the base units of all the terms on the left hand side of the equation, only then the equation is said to be homogeneous. Homogeneity of an equation is the necessary condition for any equation to be considered valid, but it is not a sufficient condition, which means that further evaluation is needed. So the first part is basically that we need to ensure that the base units of all the terms on the left hand side of the equation should be same. They should be identical to the base units of all the terms on the right hand side of the equation. So this is how we're going to check if the equation is homogeneous or not. The second thing is that basically homogeneity is essential for an equation to be considered valid. However, it is not the only condition that declares an equation as valid, so we need to check other factors as well, right? For example, we have 5 apples and we have 3 oranges. That is a total of 8 fruits. But since apples and oranges are not the same things, therefore this equation is not going to be homogeneous, because if we consider it in terms of base units, the base units would not be similar. Similarly, when we've been given energy plus power is equals to force, we know that the base units of energy are kg m square s minus 2 and the of power are kg m square s minus 3. These base units collectively are not identical to the base units of force, which are kg ms minus 2. Therefore, this equation will not be considered homogeneous. Therefore, both of the equations we've been given here are not homogeneous and not valid. Moving on to a few examples. The first one is distance. Distance is basically speed into time, right? So on the right hand side, we've been given speed into time. The units of speed are ms minus 1 and the units of time are seconds. Now when we multiply both of these units, we find that on the right hand side we have meter, because s minus 1 and s would get cancelled, so we just have meter left. So on the right hand side, the product of speed into time would be meter, and on the left hand side we have distance, and we already know that the base units of distance are meter, right? So on the left hand side the base units, and on the right hand side the base units are both meter, therefore they're identical, and therefore this equation is going to be considered homogeneous. Moving on to velocity. Velocity is basically frequency into wavelength, right? Because v is equals to f into wavelength, right? On the right hand side, we've been given frequency into wavelength. We know that the units of frequency are hertz and the unit of wavelength are meter, right? Because wavelength is a sort of length. So since we are going to be multiplying them both, we also know that frequency in terms of seconds can be s minus 1, because frequency is 1 upon f, 1 upon time, right? So 1 upon time would be 1 upon s, so that would become s minus 1, and multiplying that by the units of wavelength, which is meter, we would get ms minus 1. So on the right hand side we have ms minus 1. Similarly, on the left hand side we already know that the base units of velocity are ms minus 1. So the base units on the right hand side of the equation are identical to the base units on the left hand side of the equation. So both the base units are ms minus 1, therefore this equation will be considered as homogeneous. That the total energy is equal to the sum of gravitational potential energy and kinetic energy. We know that the total energy is basically work done, so the formula is force into displacement. The formula of gravitational potential energy is mgh, and the formula of kinetic energy is 1 upon 2 mv square. But here we have been given 1 upon 3 mv square. So since this equation would be homogeneous, which means that all the base units of all the terms on the left hand side and the right hand side would be identical, so the equation would be homogeneous. However, it would not be valid. Why it would not be valid? It is because the units of the formula of kinetic energy needs to be 1 upon 2 mv square. However, we've been given 1 upon 3 mv square. So it is only experimentally that we can actually determine whether an equation is valid or not. So we've been given L bracket 3 plus a square upon p bracket close is equals to qt square sine theta. L represents length, a represents radius, and t represents time. So the question says, given that the equation is homogeneous, use this information to find the derived units of p and q and also identify which physical quantity p and q represents. So we have already been told the equation is homogeneous. So we can assume that the base units of all the quantities on the left hand side of the equation would be identical to the base units of all the quantities on the right hand side of the equation. So first of all, we're going to rewrite this equation after removing the brackets. So as we remove the brackets, L would be multiplied by whatever is present inside the bracket. So it would become 3L plus a square L upon p is equals to qt square upon qt square multiplied by sine theta. So we know that all these terms, the three terms, will have the same derived units. Why? Because the equation is homogeneous. So we know that the unit of length are meter. So we can automatically write that 3L is equals to meter. Now since the other two terms are also supposed to have the same derived units, why? Because the equation is homogeneous. So we'll write a square L upon p is equals to m as well, and qt square into sine theta is equals to m as well. Now we'll basically solve for p. So as we solve for p, we'll make p the subject. Before making p the subject, we'll basically write the units of a square into L. So a was radius, so its units would be meter. So instead of a square, we'll write m square, and instead of L, we'll write m, because length is also in meter, right? Upon p is equals to meter. Now we'll make p the subject, and as we make p the subject, we'll find out the base units of p would be m square, right? So the units of p are m square. Moving on to the third quantity moving on to the third part of the equation, the third term of the equation, which was qt square sine theta is equals to m. We know that sine theta, sine, cos, tan, they're all just ratios, so they're dimensionless. Therefore, there are no units, so we will not include that in the equation further. So it will be insignificant for us. So now we have qt square is equals to m. Now, since we are finding out the units for q, we'll write q as it is. Instead of t square, we know t is time, right? So the units of time are seconds. So instead of t square, we'll write seconds square, and that will be equals to m, right? Now making q the subject, m will get divided by s square, so that will become ms minus 2. So earlier we got p is equals to m square, and we got q is equals to ms minus 2. Now m square, we already know that the units for area are m square, so we know that p is basically area, and q has the units of ms minus 2, and earlier we learned that the units for acceleration are ms minus 2, so therefore q is going to be your acceleration. That's about it. It says v is equals to root 2gm upon r. V represents velocity, m represents mass, and r represents the radius, and here we have to find the base units of g. Right, so we know that the units of velocity are ms minus 1, the units of mass are kilograms, the units of radius are meter. So we'll basically remove the root present here. How? We'll basically square both the terms on the right and left hand side, so it will become v square, and the root is gonna get cancelled by the square, so it's just gonna become v square is equals to 2gm upon r. Now we have to find the base units of g, so we'll make g the subject, so it will become v square into r upon 2m. We already know that the base units of v, velocity, are ms minus 1. So instead of v square, we'll write ms minus 1 square. Units of radius are meter since it's a length. So we'll write m instead of r, and upon 2m. Since 2 is insignificant here because it has no units, so we'll ignore it. And instead of m, we'll write kilograms because the units of mass are kilograms, right?
So after cutting out the quantities and doing the right math, we'll derive the conclusion that G is basically equals to kg minus 1 m cube and m cube s minus 2. So we have found the base units of G. Moving on to the next part, it says if x is equals to gm square upon r square, which physical quantity could x be? Now, since we already know the base units of G, which were kg minus 1 m cube s minus 2, we'll substitute it in the equation we've been given in part 2. So instead of G, we'll write kg minus 1 m cube s minus 2. Instead of m square, we'll write kg square, and instead of r square, we'll write meter square. And then after doing the right math, we'll find that x is equals to kg ms minus 2. At the beginning of the chapter, we found out that the kg ms minus 2 were basically the derived units for force, right? Therefore, we know that x is force. So, as a question asked is which physical quantity could x be, we know that x is force. Now we'll be moving on to the prefixes. Prefixes are very important in physics because they help us to write our quantities in a way which are easier to comprehend and to understand. Because obviously if there are a lot of zeros and a lot of decimal places, then it would be really hard to actually comprehend what the answer is exactly, right? So these prefixes make the job easier for us. So we'll be going through a few prefixes. They include pico. Pico is basically 10 raised to the power minus 12, and it is represented by a symbol of small p. Then we have nano, which is basically 10 raised to the power minus 9. It is represented by the symbol small n. We have micro, which is represented by which is 10 raised to the power minus 6, and it is represented by this tiny little symbol which I like to call a U, which is not exactly a U, but I like to call it a U, right? Then the next one is milli. Milli is 10 raised to the power minus 3, and it is represented by a small m. Then there is centi, 10 raised to the power minus 2. It is represented by small c. Then there is deci, which is 10 raised to the power minus 1. It is represented by a small d. Then we have kilo, which is 10 raised to the power 3. Now the powers are becoming positive. Earlier they were negative, so we know that it is basically becoming bigger now. So kilo, 10 raised to the power 3, and it is represented by a capital K. Then we have mega, 10 raised to the power 6, which is represented by a capital M. Then we have giga, which is 10 raised to the power 9, and it is represented by a capital G. And then we have tera, which is 10 raised to the power 12, and it is represented by a capital T. So now you just need to learn all of these according to their powers and the symbols they are represented by, because they would be used in almost all the chapters of the A-level physics syllabus. And so it says convert 300 millijoules into microjoules. How do we know that it is milli? Because earlier we learned that the small m is basically representing milli, and the U-like structure, the U-like symbol, it is representing micro, right? So when we are converting 300 millijoules into microjoules, we'll basically write 300 millijoules. So instead of the m, we'll remove the m of milli, and since we know that milli is basically 10 raised to the power minus 3, so instead of milli, we'll write 300 into 10 raised to the power minus 3 joules. So we can see that we've removed the m, and instead we have substituted it with the correct power, 10 raised to the power minus 3. Right? So we know that 300 into 10 raised to the power minus 3 is millijoules. Now, when we want to convert it into microjoules, we'll be dividing this quantity by what? We'll be dividing it by 10 raised to the power minus 6, because micro was 10 raised to the power minus 6, right? So when we divide it by 10 raised to the power minus 6, we'll basically do the right math, and the minus 6 will move up, and it's going to become plus 6, obviously. So plus 6 minus 3 would become plus 3. So it is going to become 300 into 10 raised to the power plus 3 microjoules. So now we have converted 300 millijoules into 300 microjoules. So 300 into 10 raised to the power minus 3 is basically 300 into 10 raised to the power 3 microjoules, right? So now we'll be giving the answer in standard form. So we'll move the decimal 2 places backward. So as we move it 2 places backward, it's going to become 3 into 10 raised to the power 5 microjoules. So this is the conversion. 300 millijoules is equals to 3 into 10 raised to the power 5 microjoules. Another example is that we have to convert 60 megawatt, because the capital M here represents the mega, right? So converting 60 megawatt into kilowatt. How do we know it's kilo? Because the capital K represents kilo, right? So 60 megawatt would be 60 into 10 raised to the power 6 watt. So instead of mega, we write into 10 raised to the power 6 watt. And the kilo is basically 10 raised to the power 3, right? So 60 into 10 raised to the power 6 watt would be divided by 10 raised to the power 3 of the kilo. And after doing the right math, the 3 would move upward and would become minus 3. So the plus 6 minus 3 would make up 60 into 10 raised to the power 3 kilowatt. So now we know that 60 megawatt is equals to 6 into 10 into the 10 raised to the power 4 kilowatt. How did we get this answer? We converted the 60 into 10 raised to the power 3 kilowatt into the standard form. So the decimal place was moved one step back and it became 6 into the 10 raised to the power 4 kilowatt. What exactly is the standard form? So if we have a into 10 raised to the power n, we need to ensure that a is always greater than equal to 1 and always less than 10, right? So a is represented at one decimal place. So for example, if we have a value 967234, we need to ensure that the a here, the 9 here, should always be greater than equal to 1 and always less than 10. Therefore, we'll convert it into 9.67234. The answer will be to one decimal place, and we've converted the 9.67234 into 9.67234. So we've moved the decimal place 5 places backward. For each place that we move the decimal place backward, we'll increase the power by 1. So since we're moving it 5 places backward, the power would become 10 raised to the power 5, right? So 9.67234 into 10 raised to the power 5, and obviously since it's 9.67, we're going to round it off to 9.7. So it's going to become 9.7 into 10 raised to the power 5. Similarly, we have 0.03865, right? So here the 3 needs to be the 3 is the a here, right? So it needs to be greater than or equal to 1 and less than 10. So we'll basically make it 3.865. We'll give it to we'll represent it at one decimal place. So we're making it 3.865 into 10 raised to the power minus 2. So why is it minus 2? It is because we moved the decimal place 2 places forward, right? We moved it 2 places forward. So for each place we move the decimal place forward, it becomes minus 1. So since we're moving it 2 places forward, it's going to become minus 2, right? So it's going to become 3.865 into 10 raised to the power minus 2, and then since we're going to round it off, so 3.865 is going to get rounded off to 3.9 into 10 raised to the power minus 2. So this is how we give our answer in standard form. We have to convert 60 meter per second into kilometer per hour. We know that 1 hour has 3,600 seconds, right? So when we're converting the 60 meter into kilometer, we need to divide the 60 by 10 raised to the power 3 of the kilo, right? We need to divide it by 10 raised to the power 3 of kilo. So we divide the 60 by 10 raised to the power 3, and the 10 raised to the power 3 would move up, obviously. So it's going to become 60 into 10 raised to the power minus 3, because when it goes up it would become minus, so it becomes 60 into 10 raised to the power minus 3. So that is basically 0.06 kilometer. So here we have converted the 60 meter into 0.06 kilometer. Now we have to convert the seconds into hour, right? So basically we know that 1 second is equal 1 hour is equal to 3,600 seconds, right? And we know that in 1 second we're traveling 0.06 kilometer, because it was 60 meter per second. So that since 60 meter is equal to 0.6 kilometer, so it is 0.06 kilometers per second, right?
So in 1 second we're traveling 0.06 kilometer. So how much would we travel in 3600 seconds? So it's just gonna be a ratio thing, and then we're gonna be multiplying the 3600 by 0.06, and that's gonna become 216 kilometers, right? So it is basically 216 kilometers per hour. So this is how it works. Moving on to the second conversion, which was we had to convert 216 kilometer per hour into meter per second. So how do we do that? We know that 216 kilometer would be equal to 216 into 10 raised to the power 3 meter. Why? Because the kilo here, the kilo represents 10 into the power of 3. 10 raised to the power 3, so it would become 216 into 10 raised to the power 3 meter. So that is basically 216,000 meter, right? So the first step was multiplying the 216 by 1000 in order to convert the kilometer to meter. Now the second part would be dividing by 3600, because we know that 1 hour has 3600 seconds and it was 216 kilometer per hour. So 3600 seconds had 216,000 meters, right? We travel 216,000 meters in 3600 seconds. So how much would we travel in 1 second? Now we do the same thing, except that here we're going to be dividing the 216,000 by 3600, and we get the answer 60 meter. So 216 kilometer per hour into meter per second is basically 60 meter per second. This completes the first part of the chapter. You may pause the video to ensure that you have covered all the learning objectives listed here. In the upcoming video, I'd be covering the second part of this chapter, which is errors and uncertainties. So stay tuned and goodbye.